Okay, thank you for all of you for coming in this early, and let me start by giving a warm thanks to Joe and Gaia for organizing such an awesome inaugural meeting of the Society for Computation in Linguistics, and to Joe for organizing the great symposium, and to NSF for funding it. I really do appreciate the opportunity to give this talk. I've tried hard to create a talk that you two won't regret having let me give. I hope you've all had plenty of coffee, despite the challenge, because even though it's a long slot, there's a lot of ground to cover, so I need to hold you in rapt attention. We'll see how that goes. Okay, the main claim I want to make in this talk is that strong synergies exist between the grammar of symbol structures and neural network computation. The aspect of this claim that's relevant to skill is the claim that neural network computation can strengthen the theory of grammar. The aspect relevant to the celebration of the 60th birthday of Perceptrons and Syntactic Structures is the claim that theories based on symbolic structures and those based on neural networks can actually strengthen each other. Rather than seeing symbolic and neural theories as incommensurate and in conflict, which they appear to be on the surface, I want to present a unified perspective in which symbolic and neural theories can be seen as descriptions of one and the same computational system at two levels of description, as suggested in this cartoon diagram. The tree and the activation pattern are literally two descriptions of the same computational state, analogously to how a macrostructural and microstructural description can describe exactly the same state in computer science or in physics. This is just one of a set of approaches to neurosymbolic computing that are being explored currently by various researchers. For example, we'll hear about another one from Chris Dyer on Saturday. The main claim I want to make is going to be broken into sub-claims. 4 specific claims, well, relatively specific. In part 1 of the talk, I'll argue that the combinatorial structure of symbolic representations can be implemented or realized in combinatorially structured neural representations, that is, patterns of activation over networks of simple numerical processing units, which are mathematical abstractions of neurons. In part 2, I will argue that the notion of Wellformedness that's central to symbolic theories of grammar has a counterpart within neural networks. Parts 1 and 2 show how the abstract symbolic level of description informs the lower neural level of description. Then, in parts 3 and 4, we'll show the reverse. In part 3, we'll see how optimization of Wellformedness can be a fundamental principle of neural computation, and how this can be pulled up to the abstract level to give new optimization-based symbolic grammar formalisms. And then in part 4, we'll turn to the more recent research I've been engaged in, showing how the essential gradient nature of neural representations entails that representations at the symbolic level are in general structures of gradiently active, partially present symbols. We'll look at an example of gradient symbolic grammar in French phonology. And then finally, in part 5 of the talk, we'll discuss preliminary results of current work in progress, applying the ideas of part 1 to applications in natural language processing, models of natural language comprehension and generation. This work employs deep learning and will raise the possibility that new theoretical linguistic insights might be extractable from the results of deep learning. So, to start, what is a symbolic representation? For an authoritative answer, let's turn to a foundational paper delivered at the inaugural meeting of the Cognitive Science Society by a founder of that field, Alan Newell. Newell says, each symbol structure is of a given type and has some number of distinguished roles. Each role contains a symbol. So to show the roles and the type explicitly, we could write an expression like this. See if this works. Here. We call each pair, such as Rn, Sn, a binding of a role and a symbol. To illustrate the notion of role used here, we can consider the type symbol structure, which is a string or sequence of symbols. One set of roles for this type of structure would be first element, second element, and so forth. The structural type of binary tree has an analogous set of positional roles. Or for the structure of a clause, we might adopt syntactic roles like subject, verb, and object. Now, how can an abstract symbol structure understood in these terms be realized at a finer grain level of description as a neural activation pattern? One general answer is provided by tensor product representations, or TPRs. In a TPR, the activation pattern representing the whole is the sum of the activation patterns realizing the constituent role symbol bindings. And the activation pattern realizing a constituent is the product of two activation patterns realizing the role and the symbol bound to it. For the aficionados, the relevant type of product here is the tensor product, a generalization of the outer product of vectors. A number of theoretical results show that with TPRs, networks can compute interesting symbolic functions. The foundation of these results is the recursive realization of binary trees, which can be done with perfect decodability. So, for example, a binary tree like this can be realized using TPRs as an activation vector, which can in turn be perfectly decoded to give back the original tree. In general, given the TPR for a structure, we can perform unbinding of any role. We can extract the symbol bound to that role in that structure. The activation vector realizing the tree can be passed through a simple network to give a new activation pattern, which is the exact realization of the left subtree, or passed through a different simple network to give the realization of the right subtree. This can be continued recursively all the way down to the leaves of the tree. These TPRs of trees allow networks to exactly compute an interesting class of recursive functions and to perform operations in one parallel step, such as tree adjoining in tag, or function argument application, or even basic logical inference. So to summarize part one, combinatorial representations at the symbolic level can be redescribed at the neural level as activation patterns that are constrained so as to have their own combinatorial structure. These are tensor product representations. Neural networks meeting certain constraints can then operate on these TPRs to perform computations that are describable at the symbolic level as recursive function evaluation. Now, moving to the second part of the talk, we'll ask, is there a neural level counterpart to the central symbolic notion of grammatical well-formedness? Well, it turns out that many neural networks' activation patterns can be assigned a numerical harmony value, H, where higher harmony corresponds to being more well-formed, in the sense that activation spread in the network avoids representations with low harmony, seeks out states with maximal harmony. The harmony of an activation pattern measures how well the pattern satisfies the micro-constraints that are realized by the connection weights. To see this, consider two units in a network that are connected with an inhibitory connection, a connection with negative weight, so that activation of one unit suppresses activation of the other. We can interpret this negative connection as realizing a micro-constraint, asserting that these two units should not be active simultaneously. The activation pattern shown with two active units violates the constraint, and the harmony contributed by this configuration is therefore negative. Numerically, we take the activations of the two connected units and multiply them together, then multiply that by the weight of the connection linking them. This gives a negative value, -1, for this particular pattern. And this alternative pattern over the same network units satisfies the constraint, and the harmony is resultingly positive 1. The harmony of an entire activation pattern is gotten by simply adding together the harmonies contributed by every single connection. Note that spreading activation increases harmony. For example, in the left case, each unit drives down the activation of the other, reducing the three-way product and making the harmony less negative. That is to say, spreading activation increases harmony. Now we'll put together our two results so far, that symbol structures can be realized in neural activation patterns as TPRs, and that there is a well-formedness measure over activation patterns, harmony. and ask, what does harmony maximization do with tensor product representations? The answer is, it allows us to define the harmony of symbol structures. To define the harmony of this syllable, we find its TPR realization at the micro level, exploiting our unified view that the tree and the activation vectors are merely different descriptions of the same mental representation. Therefore, they must have the same harmony. So the harmony of this representation can be computed using our formula operating at the neural level. Now, simple math will show that when the activation pattern has the combinatorial structure of a TPR, this harmony value is the sum of terms, each of which gives the harmony arising from having a particular pair of constituents in the same structure. Now, if we want, we can ignore the subsymbolic or neural level and operate purely at the symbolic level. One of the constituent pairs that we expect to find in the sum for the harmony here is this one. It combines the syllable node and the T in coda position. The harmony contributed by this will be negative, as it is an instance of a violation of the universal no coda constraint. This pair, by contrast, will contribute positive harmony, as the onset constraint tells us that syllables with onsets are preferred. The whole set of positive and negative harmony values for constituent combinations constitutes a harmonic grammar. By the principle of harmony maximization, the output of the grammar is a symbol structure that maximizes harmony, the optimal representation. So to summarize part 2 of the talk, the weights in a neural network define a harmony function that measures the extent to which an activation pattern satisfies the micro-constraints realized by those weights. This is the well-formedness of the neural representation. When the activation pattern is the TPR of a symbol structure, the harmony of the representation can be computed from the symbolic constituents alone. It's the weighted sum of violations of constraints that favor or disfavor certain constituent combinations, this being a harmonic grammar, where the well-formed structures optimize harmony. Finality theory is a limiting case in which the contribution to the harmony of each individual constraint must exceed the maximum possible harmony contribution arising from all weaker constraints combined. That's what gives strict domination of constraints. Now, if the network that we start with is stochastic, that is, has a certain kind of randomness in its spreading activation process, the same analysis leads to a grammar formalism called probabilistic harmonic grammar, or maxent in the computational linguistics literature. In these kinds of grammars, all outputs have a certain probability of occurring, but the higher harmony outputs are exponentially more likely. So actually now we have derived the third claim of our talk here, that the principle of harmony optimization can be pulled up from the neural to the symbolic level, giving harmonic grammar. So to continue on this third point, I'll go straight to the summary. At the neural level, computing the optimal representation is done by spreading activation using a particular dynamical process which consists of a force pushing to greater harmony, plus a random force that enables the system to escape local harmony optima and find global harmony optima, plus a quantization force that pushes towards all activation patterns that are exact TPRs of discrete symbol structures. Now it can be shown in the limit as the randomness parameter t goes to 0, while the quantization force and time go to infinity. The network converges to the TPR of the symbol structure that globally optimizes harmony, the correct output of the harmonic grammar. This dynamical aspect of the framework will be discussed by Matt and Pyongwan in the next talk. And for applications of this dynamics to incremental sentence processing and connections to surprisal, I invite you to check out the CMCL talk that Pyongwan Cho will be giving in this room on Sunday at 10. Okay, so now our fourth and last theoretical topic. Okay, so The activation patterns realizing symbol structures, TPRs, are special patterns. The activation pattern shown here is one of those special network states that exactly realizes a discrete symbol structure, the tree shown here. But this slightly different pattern is not the TPR of any discrete tree. All the activation patterns, aside from those realizing discrete symbol structures, can be interpreted as realizing gradient symbol structures, which are the data processed in gradient symbolic computation, or GSC. In a gradient symbol structure, a position may be occupied by a blend of symbols, each partially present or gradiently active. So this activation pattern on the right, described at the symbolic level, is a tree with a blend of Frodo and Sam in the subject position, mostly Frodo, higher activity level, and a blend of lives and died in the verb position. Harmonic grammars can assign harmony values to these gradient symbol structures. The degree of constraint violation is proportional to the activity of the violated symbols. So this is gradient harmonic grammar, GHG. At this point, GHG has been used in about 20 grammatical analyses. And if you're interested, I can send you a list of them if you email me. I will discuss just one of those examples now, a GHG analysis of French liaison. Okay, at its most basic, the phenomenon of liaison is illustrated by the word for small, which is pronounced petite before a vowel, but petit before a consonant. So now let's consider the behavior of the final T in the prevocalic environment of petit ami, little friend. We're interested in the relative harmonies of the outputs in which it is or is not pronounced. The analysis posits this underlying form for petit ami. Petit has a final gradient T. Its activity level is lambda, which will have the value of 0.5 in the particular instance of the analysis shown here. So what we have in the final position is a half-strength T. In the first position of the underlying form for ami, we have a gradient blend of the three productive liaison consonants, each with a low activity level, 0.3. The subscripts are IO correspondence indices. So now we'll consider these output candidates, which fail to pronounce or pronounce the T. The one that will win is candidate B, in which the final weak T of petit coalesces with the initial weak T of mi, yielding an underlying activity of 0.8 for the coalesced T. The gradient version of the depth constraint is violated to a degree equal to the amount of activity that Jen has to add to bring the underlying activity of 0.8 up to the surface level of 0.1, which is the surface level assumed of all segments in this analysis. The gradient max constraint is here taken to be positive, that's not crucial, rewarding underlying activity that surfaces. Then there are three other standard constraints from OT phonology here. The weighted sum of violations of each candidate, namely its harmony, is shown in the final column. The highest harmony candidate is B, so on the surface we get a medial T between petit and mi. Now, under what conditions is it optimal to pronounce this T? When does candidate B beat candidate A, for example? Well, we compute the harmony of B minus the harmony of A and ask when it is positive. The result is this expression here, where D is the weight of the depth constraint, U the weight of the uniformity constraint, and so on. The answer is that B has a higher harmony than A if the total activation of the coalesced input segments, which is lambda plus tau in this case, exceeds this quantity here. This is a threshold for this environment. Underlying material must have total activation exceeding this threshold in order to surface. Crucially, we're not adding a new concept of activity threshold to the primitives of linguistic theory. This is an emergent meta-property found through analyzing the grammar, resulting from the combination of harmonic grammar and gradient symbolic representations. Now we can follow the same procedure for all elements X and environments E, getting a corresponding threshold theta V for each environment. The activity of a gradient X must exceed that threshold to surface in that environment. Visualization of the analysis deploys a black bar as an activity axis on which we place the threshold for the given environment. Then we place the element occurring in that environment at its underlying activity level. Here, the medial T of petita mi has underlying activity 0.8. Because the activity exceeds the threshold, it is optimal for the element to surface in this environment. On the other hand, in jolia mi, the element in the intervocalic environment is just the blend of consonants at the beginning of ME, each with activity 0.3. Positioning these on the activity axis, we see that since their activity falls below the threshold, they do not optimally surface. We can do the same for about a dozen other liaison phenomena, each characterized by some type of typically gradient element in some particular type of environment. And the visualization we get looks something like this. You see there are lots of environments, lots of types of segments, and it explains quite a varied pattern of behaviors for liaison consonants and vowels that elide as well as part of the analysis. Now, the analysis here is subject to some restrictions on the patterns that it can generate. Certain implications must hold about the inventory of surfacing segments. So for example, no matter what the underlying activity of segment X is, if that segment surfaces in an environment with a threshold theta, then that segment must surface also in any environment with a threshold lower than theta. Or no matter what threshold an environment has, if a segment X with activation A surfaces in that environment, then any segment with an activation greater than A must also surface in that environment. You can read about this analysis in great detail in a paper on the Rutgers Optimality Archive here. Okay, so let me summarize the four theoretical synergies that we've discussed. Symbol structures can be realized in activation patterns of combinatorial structure, tensor product representations. Grammatical well-formedness can be realized as a harmony function evaluating the degree to which activation patterns satisfy micro-constraints in network weights. Harmony can be brought up to the symbolic level, where it defines harmonic grammars, or probabilistic harmonic grammars. The inherent gradients of activation patterns projects up to gradient symbolic representations, which are evaluated by gradient harmonic grammars. Okay, so now we are in a position to move to part 5, applications. We're going to be talking about applications that pursue only the first of these points so far. The research question behind these applications is this: can the constrained nature of structured TPRs coexist with, or maybe even enhance, the power of deep neural network learning, the results of which are notoriously unstructured and uninterpretable? I will present 2 example applications. Secondly, the generation of captions for images, and firstly, the task of text comprehension, instantiated as question answering on the Stanford question answering dataset. In which case, the task is to take a paragraph from Wikipedia and a question, and then identify the stretch of text in the paragraph that contains the answer to the question. The model that's been developed with colleagues at Microsoft Research AI is described in this paper, and I must refer you to the paper for explanation of the deep neural network architecture deploying TPRs that it constitutes. The performance of our model, which is constrained to use TPRs, is comparable to the original unconstrained model on which ours is based, whether you consider the exact match or F1 criteria for evaluation, or you look at either the development or the test set, data sets. So even though I won't go into the details of the architecture per se, here's what the model does at a conceptual level. We let the TPRs in the model use 100 symbols in 20 roles. These symbols and roles have no meaning whatever at the start of learning. The words of the paragraph and the question are fed into the model one at a time. And for each model, for each word, the model selects a symbol and selects a role. For the aficionados, I mean soft selects here. The model then takes the activation patterns for the selected symbol and role and binds them together with the tensor product, as always for TPRs. And it is this TPR role symbol binding that is sent to the rest of the network for computing the answer to the query. Now, our main interest here is in interpreting the learned representations. So we ask which word tokens select a given symbol or a given role. Our expectation was that the words selecting a given symbol will be lexically, semantically similar, have similar meanings, and the words selecting a given role will approximately be those fulfilling some grammatical role. We'll consider the roles first, and then look at the symbols. Note that we're not interpreting the actual units in the network, but rather the abstract representations of the symbols and roles that are combined to determine the activation of the actual units. It turns out that interpreting the roles involves grammatical notions ranging from features to grammatical functions. The paper goes through all these examples, but I only have time to discuss one. Role 1 is assigned to sequences, not necessarily contiguous, of words, such as how many teams, what kind of buildings, and so on. We can interpret these as an approximation to something like a WH restrictor phrase, including the main WH word, as well as a property restricting the type of possible answers. These are not always true phrases in the syntactic sense. Other examples are, what was the American? Which logo was? What's the name of the green? Roughly in practice, it seems that the sequences assigned to role 1 are the main WH word plus following words up to approximately the first content word. An intriguing question for future work is whether categories like this discovered by deep learning can suggest valuable new concepts for linguistic theory. In addition, we compared the roles that were assigned by the model with the parts of speech assigned by the Stanford parsing system. Looking at the treatment of the TV character Doctor Who, which appears many times in the data set, we saw interesting discrepancies between the two systems. The paper looks at 3 such discrepancies, but we have time to discuss only one of them. We consider the treatment of the word who. It occurs 167 times within the phrase Doctor Who. And the Stanford part of speech tagger errs on every single one, tagging who as a question word rather than as a part of a noun phrase. For the model's treatment, recall that role 1 marks the role of a WH restrictor phrase. So assigning who role 1 may be the same error, which the model does 32 times. But actually, in 30 of those cases, role 1 is in fact appropriate because who is part of a genuine W restrictor phrase initiated by a different genuine WH word, like which in a question that starts which Doctor Who, blah, blah, blah. On the 30 questions of the form who, blah, 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 Doctor Who, the model, unlike the tagger, behaved correctly on every one. For example, in who is the producer of Doctor Who, the model assigns role 1 to the first, but not the second occurrence of who. Okay, I refer you to the paper for much more discussion of the interpretation of these roles, but let me pass now to the interpretation of the symbols that are learned. And recall that we expected that the word tokens selecting a given symbol would be lexically semantically similar. So what we did for each token was to compute its symbol vector, that is to say, look at the symbol vector assigned by the model to that word, and find the most similar standard vector of the 100 numbered symbols. What symbol was it closest to? And so if we look at the words that are closest to symbol 11, we see they have a very strong relationship. Or if we look at symbol 27, we see a more heterogeneous collection of tokens, but many of them seem to refer to occupations. Or for symbol 6, again, some variation, but a lot of them refer to geographic concepts or entities. Not all the symbols are interpretable in such a straightforward way. For example, symbol 2 is selected by these tokens, and if anybody sees a nice pattern there, please tell me. We have not been able to identify one. But this process of interpreting the internal representations of the model is not just epiphenomenal. We can actually predict errors the model will make based on internal misrepresentations as interpreted here. So looking at the symbols selected for the word who across multiple contexts, we see that we can interpret these as carrying 3 different meanings. Now consider the question, what type, genre of TV show is Doctor Who? Who, in this case, should select symbol 98. It's part of the proper noun. But in this particular question, the model misselects symbol 52, which means it's being interpreted as a main question word. So we predict it will make an error. It will treat this as a who question instead of as a what question, which in fact it does. Its answer is appropriate for a who question, but not for the actual what question. We can compare the error rate when the model incorrectly assigns symbol 52 versus when it correctly assigns symbols 98 and 25. And we see a big difference in the error rates, much more frequently making errors when it misinterprets who as interpreted here. So let me just conclude this discussion of the first application by again raising the possibility that more sophisticated analysis of models such as this might be able to lead us to new concepts of linguistic theory. So now moving quickly to the second application. This paper reports this project on arXiv. Here we use TPRs in a very different way for generating image captions. Here, it's the global architecture rather than the local internal representations that are TPR informed. The architecture is what we call TPR capable, in that it is designed to be able to work with TPRs, but the representations are learned, not constrained to be TPRs. So the model looks overall like this. The input to the model is an image, which has been pre-processed by a pre-trained convolutional neural network. The output is a sequence of words. Each word is the output of a lexical module L inside the network, which looks up the word in a pre-trained dictionary of distributed activation pattern representations. The model is a recurrent neural network which has 2 other modules. The sentence module S has a representation we interpret as a static encoding of the whole sentence to be produced. If it were a TPR, if the model were brilliant enough to learn to use TPRs here, to produce a word at time t, this word needs to be unbound from its role in S. The unbinding activation pattern, or unbinding vector, to perform this would be produced by the unbinding module U. The unbinding operation, the matrix vector product, is performed here. And the result is the distributed pattern encoding the next word. So to summarize, we interpret S as encoding the caption, and U as generating a sequence of roles to unbind from S. U is like a language model, but operating over roles rather than words. The performance of the model is shown here according to a set of metrics. We get performance that is at least as good as the baseline models that use standard state-of-the-art technology, long short-term memory networks. Okay, so again, what we're really interested in is not the performance level, but interpreting the learned roles. For this analysis, we took all of the unbinding vectors used by the model to generate caption words and clustered them. We then saw that words are generated by, we saw which words are generated by vectors in each cluster and looked for the properties characterizing those words. To guide the interpretation, we considered several types of roles that might have been learned. There are positional or formal roles, like position 1 and position 2 in the caption. There are substantive roles, like role of being a noun or a subject or relative WH. There are hybrid roles like first NP or matrix verb. And for our initial analysis, we looked for position type roles and parts of speech type roles based on tags from the Stanford tagger. And what we found when we chose 10 as the number of clusters to group together all of these unbinding vectors into, was that role cluster 2 always was used to extract the first word of the caption, and role number 3 was always used to extract the second word. But the other roles had more syntactic kinds of affiliation, so by some coincidence, all the remaining odd-numbered roles were noun, phrase-ish elements, and all the remaining even-numbered roles were verbal-type elements. There's enough syntactic information in these unbinding vectors that we can predict the part of speech of a word that's generated by knowing which unbinding vector generated it to some degree. If we do that on the basis of an individual vector, our accuracy is 65%. If we have a sequence of U vectors that we use to try to predict what sequence of part of speech this will generate, we can do a lot better, getting an accuracy of about 95%. So the unbinding vectors do include, encode quite a bit of part of speech information. Finally, we noticed that there are something like subroutines in the U module. Remember, that's something like a language model predicting the next role as opposed to word. For example, it's frequently produced a sequence of an unbinding vector in cluster 9 followed by one in cluster 7, which then generated a determiner noun sequence in the caption. Or a more complicated example here is a sequence of role types that generate parts of captions that have this structure here. For example, a yellow, yellow umbrella with a man, which was part of one of the captions that was generated. And in fact, this schema, as complex as it is, was actually quite popular with the model because, in fact, of the first 100 captions, it's used actually in 27% of the cases. So, let me summarize part 5. In 2 example NLP applications, deep learning can succeed when constrained to use TPRs internally, or when operating within a TPR-capable architecture. The roles resulting from deep learning in these NLP tasks contain considerable grammatical information. Maybe someday the results of learning of these kinds of models can feed back and inform linguistic theory. And on that note, I will end. Thank you.
Great, so we have 15 minutes for questions.
Yes.
Oh, are we supposed to say who we are?
Oh, yes, please do. So say your name and affiliation, please.
Christine, UMass. So I wanted to better understand where restrictiveness comes into play here. So restrictiveness of what becomes well-formed. So you talked about restrictiveness in terms of constraining things to be TPRs. I'm wondering how that relates to restrictiveness that people have looked at in terms of, let's say, the structure of constraints. For instance, if they're gradient or categorical, or where they fall in let's say, a regular hierarchy, so those kinds of restrictions, or also, let's say, in rewrite grammars, how restrictions might come about and how the derivation is constrained, again, for instance, in terms of the Chomsky hierarchy, or whatever you might be interested in. So yeah, how
Okay,
is
well,
the restrictiveness are related to those kinds of restrictiveness, or are they orthogonal and so forth?
Well, as far as I've been able to tell so far, they are pretty orthogonal in the sense that the kind of restrictiveness I was talking about of constraining activation patterns to be TPRs is at a lower basement level of linguistic theory. So linguistic theory just takes it for granted that we have symbolic representations, and it asks how are they restricted. But if we're using neural networks, then we have to first be able to restrict the use of the neural networks to be able to support representations of which have combinatorial symbolic structure. So that's what that restriction to TPR structure is about. I don't know of cases where the fact that these symbol structures are represented in this way at the neural level brings with it some implications about the computational complexity of grammars, or the nature of the constraints that evaluate them. It would be great if that were to happen, but so far I haven't been able to make it happen.
So then the idea is that you could have restrictions from that kind of work and restrictions at the neural network level together?
Right. So we saw one little example of that here. Well, not so little, actually. I mentioned that optimality theory is a kind of extreme case of harmonic grammar, where if you rank the constraints by their numerical weight, then what you see as you go up is that things grow very fast, exponentially, essentially, in weight. So you might say that the success of optimality theory tells us that there's a constraint operating, which can be summarized at the symbolic level by saying that there's strict domination among grammatical constraints. But then at the lower level, this translates into a restriction on numerical strengths, which is not inherent in the architecture itself. We'll hear a talk by Giorgio and colleagues, Magri, arguing that, in fact, there may be some reasons to derive that kind of strict domination relation coming from learnability. And when I understand their analysis, I'll see whether we can actually try to apply it at the neural level. Yes, Chris.
I'm curious.
Name?
Sorry. Chris Geyer, DeepMind. I am curious if you looked at, did this analysis, which is, I love this, but on sort of more traditional LSTM, say, back decoders for this task, say, and just what pops out there, because as far as I know, nobody's done something like that.
Right. No, that's a very good question. I wish I had the answer. The analysis that you saw was done with painstaking hand labor, and has not been repeated for an LSTM type model, but we're trying to develop tools to make that kind of interpretation much faster and more automatic, at which point we'll be able to address that question. But it's absolutely to the point to ask whether the TPR structure is responsible for this kind of interpretability, or whether it would be there anyway. Yes?
Jacob Andreas from UC Berkeley. So points 2 through 4 there all really rely on this harmony criterion, which is this sort of variational thing, right, that looks very little like what sort of modern neural networks look like. It doesn't show up in the applications that you had at the end. What are the prospects for integrating that in? You know, is there an obvious way to do that with modern machinery, or do we need new tools?
Well, I first explored networks that do harmony maximization in the context of restricted Boltzmann machines, as they're now called. So it's not entirely true that modern generation machine learning doesn't use networks that operate on that kind of principle. So the answer would be that to the extent that those kinds of network modules can be used, then there'll be some relevance of this kind of analysis to them. But I take your point that in the last example, and to the extent that that's typical of NLP models these days, it does not directly apply. But that's so much the worst, I think. Any other questions? Yes.
Chris Kennedy, Chicago. So on the NLP section, so I understand the point was to just sort of see what kinds of representations your systems were producing and see whether they had sort of more interesting structure than what we get from the deep learning models. But so that the actual performance was, as you said, kind of irrelevant. But it's kind of interesting that the actual performance was so similar to the performance of the systems without the TPRs. And so, I mean, I wonder if you have any speculation about, is that just because this was sort of a first stab at this, or if you kind of push on this a little bit further, is there an expectation that you might be able to improve performance in some way? Or is it really just about this other interesting question, which is seeing what kind of structures we can pull out?
Well, there's certainly hope on our part that incorporating TPRs into deep learning models will actually enhance performance on the right kind of task. Because we have independent reason from symbolic linguistic and NLP theories, independent reasons to believe that combinatorial symbolic structures are very powerful for doing language analysis. And a network that has that capability should be able to blow away a network that doesn't. We haven't seen that yet, but so far we've looked at only 2 tasks. One fact about applications in NLP these days that I imagine you're aware of is that everything is crucially dependent on what task is being assigned to the network. And if you ask, what task was Chomsky doing in 1957 when he proposed these kinds of structures? It doesn't resemble what these networks are trying to do very much. And so a number of people are trying to develop tasks which more closely target the kinds of knowledge that linguistic theory has posited. And my hope is that when we have tasks like that at hand, that we'll be able to do a lot better than competing models that don't have combinatorial representations available to them. Could be that we're in for another surprise, that's not true. Another surprise because I never thought that unstructured neural nets could possibly do anywhere near as well as they do. So there's some deep mystery to be solved there. And that mystery will just become even deeper if it turns out that TPRs don't give us enhanced performance, just mostly comparable performance.
I might interject right now just an ad for the talks by Chris Dyer, Sam Bowman, and Jacob Andreas tomorrow. They're all on the theme of, do hierarchical representations help in NLP tasks using neural networks? And it turns out the answers are really quite subtle and interesting. So yes, that's an ad for tomorrow's session. Yeah.
Yep. Yes.
Yes, hi, Brendan O'Connor, UMass. So I was wondering if another aspect to the symbolic versus neural, you put them as a dichotomy, is that symbolic methods, there's a place for linguistic knowledge to come in. So, a hand-designed, grammatical category system or something. Is that something you can incorporate here, or is that something that's bad and we shouldn't do? We should just be doing more pure, unsupervised learning of what the combinatorial categories are.
I'm fundamentally much more of a linguist than an NLP person, so I would never say that's a bad thing to do. The models that we have for incremental sentence processing, for example, that Pyongyang Cho will talk about, and the models that Matt will talk about in the next talk, all involve hand coding networks to include grammatical knowledge. So it turns out that, for example, context-free grammars can be translated into network patterns of connections, such that the harmony associated with activation patterns, which are the TPRs of grammatical trees, have higher harmony than activation patterns of other trees that are not grammatical. So it's definitely possible to incorporate that kind of knowledge. And so we could imagine using that as a kind of a way of initializing deep learning networks to have a lot of sensible knowledge to begin with. And then we can let deep learning destroy it to whatever extent it chooses to do.
Any more questions?
Okay, well, thank you very much.
Thank you, Paul.